Swayam Prabha. Digital India. Educated India.
The next presenter is going to be presenting in developing long-term quality multi-step prediction models for early warning. So over to you.
Afternoon to everyone here. I am Li Shan from the Department of Chemical Engineering of Chongyuan Christian University. Today, I would like to present a topic on developing long-term quality multi-step ahead prediction models for early warning. First of all, let me explain why does the multi-step prediction is more applicable than the step-ahead prediction for early warning. Look at the two graphs here. This graph shows the behavior of the process variables, and the graph above shows the behavior of the quality variable. In step-ahead prediction, the past process data and the past quality data are used to estimate the quality data at the next time point. However, there are strong nonlinearities, slow dynamics, and uncertainties inherited in the large-scale chemical plant. When fault occurs, it will not influence the process instantly, but will react after a few time points. Hence, the disturbance cannot be identified, and the estimated quality at the next time point is still in the normal rating operating region. The purpose of early warning is to detect any problem with the currently running process as early as possible. However, the conventional approaches do not care about early detection before any disturbance significantly affects the process. So to estimate the disturbance propagated through the process, a multi-step quality prediction model is essential. Instead of estimating the future quality data point, the future quality data trend is estimated. Here comes the research motivation for this presentation. The quality data, such as the concentration of the distillate, is often expensive and time-consuming to be acquired, as they are usually analyzed in the laboratory. We wish to develop a multi-step predictive model so that we can use the easy-to-measure process variables, such as the temperature, pressure, or flow rates, to estimate the trend of the future quality. So here is the brief idea of the multi-step prediction system. We will first construct a multi-step prediction model to predict the future process outputs from process inputs. Then a quality conversion model will be constructed to represent the static relationship between the future process outputs and the future quality data. With the combination of the multi-step prediction model and the quality conversion model, so early warning is done. So for the problem formulation, U represents the process inputs and X represents the process outputs. Y represents the quality variables, but some of the quality is missing due to the difficulty in obtaining the quality data during production. Corresponding to the multi-step system, multi-step prediction system, by using the multi-nonlinear process variable prediction model, the past process inputs and the past process outputs are used to predict the future process outputs. Then, in the quality conversion model, the future process outputs are used to estimate the future quality variables. The multi-nonlinear process variable prediction model is called the nonlinear state space model, multi-NSSM. It is developed based on the state space model here. The objective function of the multi-NSSM is defined to maximize the conditional relationship from the past process variables to the future process outputs. Hence, the variational inference and Bayes rules are applied to derive the variational lower bound, and this is the variational lower bound to be maximized. And this is the model structure of the multi-NSSM. The Carroll divergence term here represents the distance between the posterior and prior distribution of the past latent data conditioned from the past process inputs and outputs. To calculate this term, the past process inputs and the past process outputs are sent into the bidirectional RNNs, and it outputs distribution of the past latent data. Then the KL divergence term here represents the distance between the posterior and prior distribution of the future latent data conditioned from the past latent data. To calculate this term, the past latent data are sent into the sequence-to-sequence encoder-decoder network, and it outputs the distribution of the latent data. After that, the future latent data are sent into the emission network and outputs the distribution of future process data. Hence, the likelihood term here can be calculated according to this emission distribution. So after the multi-step prediction model for the process variables is explained, now is the turn of the quality conversion model. The quality conversion model is called the regression VAE. It is developed based on the latent variable model here. The objective function of the regression VAE is defined to maximize the joint relationship of the process input and the quality variables. Hence, this is the variational lower bound derived from the best inference, and it has to be maximized to train the model. And this is the model structure of the regression VAE. The divergence term here represents the distance between the posterior and prior distribution of the latent data. To calculate this term, the process outputs are sent into the encoder model and the outputs of the distribution and outputs the distribution of the latent data. After that, the latent data are sent into the decoder networks and outputs the distribution of process and quality data. Hence, the likelihood terms here can be calculated according to these decoded distributions. To combine the multi-NSSM and regression VAE model, the past process inputs and outputs are sent into the multi-NSSM model and outputs the future process outputs. Then the process outputs are sent into the regression VAE to estimate the future quality data. With the future quality trend, the yearly warning system is used to check the operating status. If the future quality trend falls out of the bound, it means that the process is operating at the unhealthy condition. So here, to test the monitoring performance of the proposed yearly warning system, the industrial ammonia simulation case is shown here. There are 19 process variables and 1 quality variable were collected in the historical data set. The sampling rate of the process data is 1 minute and the sampling rate of the quality data is 30 minutes. The data set are separated into 90% of training data and the remaining 10% of testing data. Thus, there are 2,100 of process data and 70 of quality data. So these plots here show the behavior of the process variables. In the process variables, there is an occurrence of fault at the feed flow rate. The fault happens at the 677 time point and 1,895 time point. This is the behavior of the collected quality variables. Unlike the process variables, the quality variable is usually difficult to be obtained. In this case, the quality data are measured at every other 30 points. So the rate at every other 30 points, the red dashes line represents the desired specification of CO2 concentration, while the both black lines are the upper and lower bounds that define the normal operating condition. Although the faults occur at the 677 and 1,895 time points, because of the large scale and slow dynamic transition nature of the ammonia synthesis process, the visualization of the faults on the quality variable emerged at the 780 and 1,890 time points. Therefore, the sample points of 780 to 1,350, this region, and the region of 1,980 to 2,070, and in this region are significantly out of specification. So the purpose of the multi-step prediction is to observe the impact of faults on quality variable in advance. So after both of the multi-step prediction model, the multi-MSSM and the conversion model, which is the regression VAE, are completely trained, the multi-step prediction system on quality is ready to perform early warning. So the quality trend in the first time step prediction point of view are shown here. Zooming the black box to see the details. As mentioned previously, the fault occurs at the 1,890 time point, and the impact on the quality variable can only be found through the offline laboratory tests at the 1,980 time point. So although the fault happens at the 1,890 time point, it's possible for any monitoring model to detect the fault at that moment because of slow dynamic transition. So by using the proposed method and with the viewpoint from the first time step prediction, we can detect the fault at the 1950 time point. This means that we can discover the abnormality 30 time points earlier. So next, looking into the five step ahead prediction point of view, note that the x-axis represents the prediction steps. This is the 5 quality predictions at the 1,900 time point. Because of slow dynamic transition, again, there is no sign of abnormality at this moment. So this is the 5 step ahead quality predictions at the 1,949 time point. Zooming in to see the detail, the quality slowly deviates from the normal. So at the time point of 1,950, all of the 5 predictions is out of the upper bound. So this is a very strong evidence to show that the process is not in the normal operating condition. So no matter from the first step prediction of the multi-step prediction point of view, the proposed method can detect 30 time points earlier than the time we got the result of the offline laboratory test. Next, in the conclusion, the integration of 2 deep neural network models can make the multi-step quality prediction system established with a small amount of quality data. Next, the multi-step NSSM developed as a probabilistic model can well describe the uncertainty of the process, while the multi-RNN cannot. From the industrial case, the impact of the fault disturbance can be identified in advance to achieve early warning of abnormal operating processes. So this is all of my presentation. Thanks for listening. Questions are welcomed.
Thank the speaker first. So the speaker is online. Any questions?
Yeah.
Any questions?
Yes.
Okay. So I had a question for you. So if you see, you're trying to predict the trend, right? So
Yes.
if you're, what about uncertainties or operational changes, operation point changes in the system? How do you account for? Because this is an auto encoder. Although it's a deep network, if the operating point changes, how do you accommodate that in your prediction of the trend?
You mean when the operating condition change, how
Yes.
do I detect
Yeah,
the
yeah. When the
operating
operating
change?
condition changes, will this algorithm, will your approach work?
You need to retrain a model to fit the other operating condition,
So then,
because once the model is trained, it is only fit the specific operating condition. So when the operating condition change to the another, of course you have to collect certain amount of data. Only you can confirm that the process condition is changed. If one time point is out of the boundary, you cannot say that the operating condition is changed. You have to at least maybe 100 or 1000 time point is out of the bound, or
no, no,
and
no,
then you can say
no, no, no.
that.
I'm not talking about the trend. I'm saying if suppose the feed, whatever to the distillation column, it changes. Now you have to build a different model, right? When your operating condition changes, it's
Yeah,
normal, but it has changed to a different condition due to various reasons. Then you have to build a different model. Is that right?
yeah.
Okay. My second question is, how about feed uncertainties? If there are uncertainties in the feed and other uncertainties in parameters, in variables or variations, fluctuations, have you tested your methodology for uncertainties?
Maybe I can try it.
Okay. Okay. Yeah. Thank you.
Okay.
Thank you for a nice
Okay, thank
talk.
you.
Once again, thank the speaker, and we'll thank you.